Let's move to our second talk. Our second title of our talk is Recent Sponsored SPTC-OU Research on Bridges in Extreme Environments. Authors are Floyd from the University of Oklahoma and Micah Hale from the University of Arkansas.
Good morning. So my name is Royce Floyd. I apologize that you're getting second string because, as you can see, Dr. Micah Hale is not with me this morning. He had something come up. He wasn't able to make it down here. But today we're going to talk about a few projects that were recently sponsored by ODOT and SPTC. We won't have time to talk about everything in great detail, but hopefully enough that you'll want to come ask me questions or ask Micah questions or ask the students questions. It should be a lot of fun. So our outline today is that we're going to give just a little bit of an introduction of why we're talking about these particular topics in Oklahoma and Arkansas, kind of the two states working together on these projects. And specifically, we're going to discuss some experimental testing we did of pre-stressed concrete girders with corroded ends, both some taken out of actual bridges, some that we created in the lab. We'll also talk about a little bit of a field study that we did to try to look at the prevalence of that kind of deterioration in bridges, and then a pretty good study that we were able to do looking at temperature effects on pre-stressed concrete girders. And then finally, hopefully spend just a minute talking about where we can go from here based on this work. So as we probably have all heard, a lot of the bridges in the United States are getting toward the end of their design lives. If you look at the latest report card from ASCE, about 40% of bridges are more than 50 years old, and another 15% are about 40 years old. So in the next 10 to 15 years, we're going to have a lot of bridges that are reaching the end of what would have been their design life of 50 years. And so we want to try to understand what things are affecting these bridges, how can we help them to potentially last longer, how can we do some rehabilitation to get some additional life out of these bridges, or which ones do we really need to put our attention on. So there are a lot of items that affect condition in addition to just aging. We have traffic demands, larger trucks, just more cars on the road. The different materials are going to respond differently over time. And then there are a lot of different design details or changes in design codes that can lead to bridges being insufficient, say, on a technicality, so to speak. But seeing as how that SPTC had a big influence on, or a big emphasis on climate, what about the changing climate within the U.S.? And if you look over on the far right, you can see a map from NOAA that shows the number of days over 100 degrees across the country back in 1979, moving up to close to today, and then a projection for the future. And as you can see, the more orange and reds on there are indicating that we're getting more days of really hot weather. We've also seen over the last couple years, more days of really intense rainfall, flooding. We're seeing more of these extreme events. And so what impact are those going to have on our bridges? And specifically, looking at temperature, what's that do to the temperature variation gradients within our bridge beams? What does that rain do to the ends of our bridge girders? What do more days of really cold temperatures do to the ends of our bridge girders? So in looking at these two questions, the first one being the end regions of our girders, and it seems hopefully kind of obvious that if we have deterioration of our bridge beams, that could lead to some problems. But specifically around our joints, we tend to get some leakage from the bridge deck. So we get water coming through those joints, falling onto the end of the girder. That's a region of our pre-stressed girder that has a whole lot of steel in there. We have steel for shear reinforcement. We have steel to resist the pre-stressing force at release. We have the pre-stressing strands themselves within our girders. Those all are susceptible to corrosion. And if we have de-icing salts on those bridges, then that's just going to make the problem worse. Then looking at temperature, if we think about a bridge girder and it being heated by the air around, we're going to have convection heat, we're going to have direct solar radiation coming straight down, and then we're going to get reflected solar radiation off the ground. That's going to cause differential heating of our bridge girders. So the top may be hotter than the bottom, the left side warmer than the right side, etc. And that can be a real problem during construction. And if you look over here on the right side, horizontal temperature gradients can cause some lateral instability that if we don't account for in design correctly, we can have potentially some failures during construction. And that's the kind of thing that we wanted to look at in this project. So looking at the design specifications for temperature gradients, the first design gradient was established back in 1989, included in the LRFD bridge specifications when we switched over from the standard specifications. It's been modified over the years as various research has come out. But if you look in the commentary of the AASHTO specifications, it even says that if experience has shown that neglecting a temperature gradient in the design of a given structure has not led to structural distress, the owner may choose to exclude the temperature gradient. So potentially we're even given an out if we've never had a problem before. But what if in this new environment of more extreme temperatures, we may have some problems that we didn't have before? So we need a better understanding of what these temperature gradients look like and what they're going to do to our bridge girders. If we think about the different regions of the country, we have two different exposure sites within Zone 2 here in Oklahoma and Arkansas for our study that I'll talk about here as we go. But the important thing that we want to emphasize on temperature effects, concrete doesn't like tension. Concrete is weak in tension. If we get unexpected tension, that leads to cracking. And temperature gradients within our girders can give us up to, or a tension stress up to 60% of the concrete strength based on previous research. Combine that with the other stresses going on in a bridge, we may get cracking. That reduces the moment of inertia or stiffness of our girders, which can lead to additional upward deflection from the pre-stress, or what we call camber, which can lead to a nice roller coaster ride if we go over a multi-span bridge. And by nice, it's actually not nice, it's rather unpleasant. So we would like to avoid that if we can. And so looking at some of the previous research, there was a study in 2010 by Lee at Georgia Tech that investigated how well this AASHTO model predicted temperature gradients within pre-stressed eye girders, because it had a lot of development from box girders. And what they found was, looking at an AASHTO BT63 girder in Atlanta, Georgia, so a fairly deep girder in a little bit different temperature environment than in Oklahoma and Arkansas, they found that the design model really didn't provide that great of a prediction. So if you look down here on the right, it has a similar shape, but there was a significantly higher temperature range than what was shown in the AASHTO model. So with those things said, the objectives of our studies, so I'm going to talk about three different studies here, were to look at what in-region deterioration does to shear capacity of our pre-stressed girders. And then also looking at what is the effect of temperature gradients on our AASHTO eye girders, or really what does that temperature gradient look like, both in the vertical direction and in the transverse direction across our girder cross-section. And then in that study also, can we determine if those gradients, or the worst gradients, we'll say, are caused by specific environmental conditions? Are they caused by the geometry of the shape? Or is there something else going on that caused those maximum gradients? So at the University of Oklahoma, we took the lead on looking at the end regions of our pre-stressed girders, and we started this with two full-scale bridge girders that were taken out of the I-244 bridge over the Arkansas River in Tulsa. The initial motivation of that project was to look at just shear capacity of older girders. These had been in service for about 46 years when they were taken out of the bridge. They were designed under a design code different than what we're using today. And there are a number of bridges in Oklahoma that have some issues relative to shear if they were designed with that old code. We tried to pick girders that were in really good shape, so we'd have a nice representation of what's out there in the field. but there was some minor damage on one end of each of these girders where they were sitting under those expansion joints. So we were able to do 4 tests, so 1 test of each end, and we found that on the first test, where we had some minor corrosion, and you may or may not be able to see it, but there's just a little bit of staining visible around that pre-stressing strand. There's a little bit of cracking around this pre-stressing strand. But during that test, we observed a slip of our pre-stressing strands before we got to failure. And we ended up with what we call a bond shear failure. So the loss of bond between the steel and the concrete contributed to the failure. If we looked at the south end, which didn't have any visible corrosion issues, we actually were testing closer to the end, so shear should have been more of an issue, but we failed that girder entirely in flexure. We actually ruptured the pre-stressing strands, which we can see over here. Our pre-stressing strand is actually visibly broken there. Looking at our second girder, and the girders A and C were the design labels. We do know the alphabet, but we didn't test a design B, so it wasn't included in our titles. But in this one, or this end, we had more significant transverse cracking to our pre-stressing strands that was there before testing. There was some additional staining around the pre-stressing strands. And in this case, when we loaded this girder up to a level equal to what it should see in service, we started to see spalling in that location. We started to measure pre-stressing strand slip, and we again got one of these bond shear type failures. For the other end of that girder, we had, again, no visible corrosion damage. We did see some very minor pre-stressing strand slip, not a whole lot. And we had a compression shear, almost flexural failure there on that end. All right, so what did we learn from these tests? We learned that in this case, the strengths of these girders were actually very good. They compared very well with what the design code said they should. They exceeded what would have been the demands on these bridges, but this even small amount of corrosion damage at the ends led to some effect on the failure mechanisms, and potentially, if it got worse, which a lot of bridges potentially have worse problems, it could affect the capacity of our girders. So to test those effects, we built some of our own girders that were half scale on this same or of this same type of design. We exposed them to a very aggressive corrosion environment of a salt spray that was off and on about every 2 hours. And we looked at some different time exposures to try to quantify the effects of different levels of corrosion on the capacity of these girders. So we tested an exposure of 2 months, 4 months, and 6 months, and we still have some out there that are getting sprayed. It's been almost 3 years now because our results didn't quite turn out the way that we expected. So this was our shear test setup, very similar to our full-scale tests, only smaller, obviously. But if we look at the results, we'll see a couple of interesting things. Okay, one is if we look at expected shear, which is the first 2 bars on each group there, we notice that they're much higher than the actual values we measured. Okay, and that is a little bit misleading because we designed these beams to fail in a bond shear type failure so that we could try to quantify the effects of corrosion on the bond between the steel and the concrete. But the other thing that you'll notice is that third bar here is higher than the fourth one in almost every case. And what that shows is that white bar is the corroded end, and the dark hatch bar there is the uncorroded end. And so we actually saw a higher capacity for the beams that had some corrosion level, which was not what we expected at all. However, the corrosion that we were able to get in 6 months was pretty minor. And that's why we held off on the others and have kept spraying them for longer times so that we can try to get closer to a real field condition, which inspired us then to say, what is a real field condition? So we identified 19 bridges in Oklahoma that were from the same time period, designed and built between 1960 and 1979 with the same design code, and had varying superstructure ratings. So somewhere, I think around 4 up to, I think about 8, somewhere in that neighborhood. So some that were really in really good shape, some that weren't in such great shape. We went out to see if we could tell anything about the end condition of the girders in these bridges. And we found some common characteristics. In almost every bridge that we looked at, we found some level of corrosion in the bearing plates and anchor bolts. And in most of those cases, the anchor plates or the bearing plates are embedded into the beam, which led to some spalling in the concrete right above that bearing plate. And then in almost every bridge, we saw some, at least minor, exposure of pre-stressing strands and reinforcing bars within the beams. So very similar to the full-scale beams that we tested. It wasn't all that extensive. However, in some cases, it was much worse. These are pictures of the worst bridge that we looked at, which had a fairly large amount of the pre-stressing strands exposed, which could have a much larger effect. All right, so stay tuned. We're still testing beams down at OU that have larger amounts of corrosion damage to hopefully be able to quantify, what happens if we have a strand that's partially embedded in concrete, partially exposed. How much is it going to contribute to the capacity of our girders? So conclusions that we had, again, there's no need to sound the alarm bells. The full-size, full-scale girders we tested had adequate capacity, but their behavior was affected by the corrosion levels that we saw. We're still studying why the corroded ends of our small-scale girders had a higher capacity than the uncorroded ends. And then there are a number of common deterioration mechanisms throughout Oklahoma that justify some of these additional studies. All right, so moving on to this temperature study that I spent a lot more time talking about the background of because it has turned out some really interesting results. But in order to look at temperature gradients within the beams, again, motivated by this idea of having more really high temperature days in Oklahoma and Arkansas and across the country, we built 5 4-foot sections of ash toe girders. So we built 2 4-foot sections of a type 2 girder, 2 4-foot sections of a type 4 girder, and 1 4-foot section of a type 5 girder. So different depths of our pre-stressed girders. We had 2 sections exposed down at Fierce Lab on the University of Oklahoma campus, and we had the other 3 at the University of Arkansas in Fayetteville. All were oriented east-west, which has been shown in previous research to have the largest effect because you get the southern exposure of the sun longer during the day. And then the girders were left in the pre-deck placement condition. So there was no deck put on these sections because, again, in previous work, it's shown that you have a lot of the biggest problems before you get the shade of the deck on top of those girders. So here's some pictures of construction of the girder segments. They were all built by the grad students at the University of Arkansas and at OU. We had wood formwork. The concrete at Arkansas was mixed by the students. The concrete out here at OU we had brought in from DeLisi, but it was all a very similar concrete mix so that we would have as close to the same materials as we could get. We monitored temperatures throughout the cross sections, both vertically and horizontally. We had 12 internal and 19 external thermocouples to measure the temperature distribution throughout the cross section. We found that the external thermocouples didn't give us very good results, honestly, but the internal ones gave us very good results, and I'll talk a little more about that here in a minute. But here's a picture of one of the fully instrumented girders, or girder segments. We have external thermocouples up and down the outside here. The internals are obviously inside, and they're all connected to a data acquisition system powered by a solar cell that recorded data every 10 minutes for about a year. We insulated the ends of the girders as well as the lifting hooks coming out to try to reduce any effects of the fact that these were really short compared to actual girders. We don't want to have additional heat transfer through the ends if we can help it. And then even though they were raised off the ground, they were pretty close to the ground, so we put a non-reflective sheet underneath them to try to reduce the reflected solar radiation. All right, so let's look at some measured vertical gradients. And you may or may not remember the shape of the AASHTO design gradient. I'll show it to you on the next slide, so don't worry too much. But looking at the internal vertical temperature gradient for the Type 2, Type 4, and Type 5 girders, we actually see that instead of having the highest temperatures near the top of the girder, we have the highest temperatures near the bottom of the girder, which was, again, somewhat unexpected. If we compare those to the AASHTO design, which is the orange line down here, we see that it has a very different shape than what we expected. If we compare those to the Lee et al. Study in 2010, which is the green line, we see that it's closer in some cases, but still has a very different shape. The other thing to note here, these are the maximum temperature gradients that we measured, which they were not for all the girders occur on the same day. They were not on the day with the highest temperature. They were actually on the day that had the largest temperature swings, which if you have spent much time in Oklahoma, you know that those can be pretty significant. It's the same way in Arkansas. And the third interesting thing is all of our maximum temperature gradients occurred at the Arkansas exposure site, not at the Oklahoma exposure site. One question is, why is that? And one thing that we have been able to identify looking at the weather conditions on those days, it's much windier in Oklahoma than it is in Arkansas, which helps to reduce some of that thermal gradient. And again, because those profiles looked so different, we wanted to have a sanity check, try to verify that that was a correct answer. So we measured strain across the depth of the girders using externally mounted Dimick gauges. We measured expansion over the course of a day, looked at the comparative internal thermal gradient, so note internal versus external, so you should expect a little bit of difference. But we found, based on back calculating temperature change from the coefficient of thermal expansion, a very similar profile for both cases, which helped verify that our temperature measurements did make sense. So we proposed a couple of potential design gradients, both vertically and horizontally. I'll show these up here. Most of you are probably not real fired up about the specifics, but if you are, come and talk to me. I'll be happy to share those with you. But again, we have this. The first one was the vertical gradient. This is the horizontal gradient, which again can lead to those stability concerns during construction. So the last couple slides, the conclusions from our temperature gradient study were that the largest gradients did not coincide with the highest temperatures, which we didn't necessarily inspect, but with the highest variation in temperature over the course of a day. The current design standards didn't accurately predict those temperature gradients for I-shaped girders. And then depending on the thermal gradient, the level of difference that we observed could cause you some problems relative to camber. So what are we continuing to do? What do we need to do? We need to look at those longer corrosion exposure times with more damage so that we can try to quantify the effects of corrosion on the bond capacity. We want to look at what happens if we repair one of those girders. We're currently looking at repairing corroded ends with ultra-high performance concrete, which is pretty exciting. And then there needs to be more examination of thermal gradients, including what happens if we put a deck into place, what happens if we raise that girder up in the air higher, and then also doing some finite element modeling for comparison and to extend to other sections. So acknowledgments, there are a lot of students that worked on this project. I don't want to leave them out. Their names are up there. If you see them, ask them questions. They'll have all kinds of answers. And then thanks to SPTC and ODOT for sponsoring this work, and to DeLisi and others for providing materials. So thank you.